Okay, this video is for AP test review number 7. Alright, a student is doing an experiment to calculate the enthalpy of solution of calcium chloride. The student places 200 milliliters of calcium of water in a calorimeter, then adds 26 grams of calcium chloride. The following data was collected. So it says calculate the number of moles of calcium chloride. So the first thing is we would start off with our 26 grams of calcium chloride. And we would just change that to moles. And so 1 mole calcium chloride, and then it's 110.98 grams is the molar mass of calcium chloride. And so that ends up being 0.234 moles calcium chloride. All right, now the next part says calculate the kilojoules of energy evolved when the calcium chloride dissolves in water. So it's asking for the energy that's going out. Okay, you can see the temperature goes up, so the energy is flowing from or into the water. So anyway, what that type of question is a Q equals MC delta T. Q equals MC delta T. So Q equals, now whenever you're doing the enthalpy of solutions, a big mistake is not doing the mass right. The mass has to be the mass of the water, which is 200 milliliters is 200 grams, plus the mass of the chemical that you're adding in. So that's 226.0 grams. Okay, so that's an important part because a lot of people forget to add the chemical mass to that. Times the specific heat, we're just going to use water specific heat, 4.18 joules per gram degree Celsius, times the temperature change. Okay, temperature change is a place where AP might check to see if you do significant figures correct. And so basically it started off at 21.8. That's where it started, 21.8. And it ends up going to 41.5. I know it's a little bit hard to see, but 41.5. And so if you subtract those numbers, it ends up being 18 point, or no, not 18. It ends up being 19.5 degrees Celsius. Notice that with significant digits, it goes by decimal places. These go to the 10th, so your answer should go to the 10th. Okay, so we're going to multiply by that by 19.5 degrees Celsius. And when we do that, we get 18,421 joules, but we want to convert that to kilojoules. So in 1 kilojoule, there's 1,000 joules. Basically, you're just moving the decimal 3 spots to the left. And since the temperature has 3 significant digits, we'll just round it to 3. So it's 18.4 kilojoules. That's what you would get. All right. Now, then it wants the enthalpy of solution. Okay, now I didn't put in here, but usually they want that in kilojoules per mole. So you take the kilojoules that were evolved, 18.4 kilojoule, and you want to divide that by the moles of the chemical that you put in it. So you're going to divide that by 0.234 moles. And if you do that, you end up getting 78.6 kilojoules per mole. Now, here's an important part, and the important part is use your brain here. Okay, when you get an enthalpy of solution, that's a delta H value, and delta H values always have to have a sign with them, or I guess if there isn't a sign, we assume it's positive, but you always got to put a sign with it. Now, just use your brain. When you added the chemical to the water, did the energy go in or out of the system, the water and stuff dissolving? And so you can see the temperature goes up. And if you're ever doing a reaction or a dissolving in a beaker and the temperature goes up, that's exothermic. So that's exothermic. That means that your number has to have a negative sign. Okay, that's very important here. Okay, so the enthalpy of solution is negative 78.6 kilojoules per mole. The negative is very important. Okay, if the temperature goes up on a problem like this, it's going to be an exothermic process. Put a negative sign on it. If it goes down, it's endothermic, positive sign. Okay, endothermic or exo, we kind of already talked about that. Okay, now this says, explain your answer using the forces involved in the dissolution process. Okay, so if you have like a crystal of calcium chloride, okay, calcium and chloride, calcium chloride, okay, just pretend I could draw one of those good, okay, and also we're putting it in water. Remember, water will hydrogen bond to itself, okay. All right, so that's supposed to be a water molecule. That's supposed to be a water. Okay, now there's a hydrogen bond between them. Okay, now basically the left side of dissolving, like you have to break apart the forces, the Coulombic attractions between the calcium and the chloride ions. You have to break those apart. Okay, that's endothermic. So it's always like energy to break the bonds. So you got the energy required to break apart the calcium and the chloride ions, and the energy to break apart the attractions of water, minus the energy released when bonds form. So subtract the energy released when bonds form. Okay? And so basically you're going to get like a calcium ion, we'll just call that the positive ion, and you're going to get chloride ions, negative, but they're going to be surrounded by water molecules. And when the water makes these ion dipole attractions to water, okay, that's going to release energy. Okay? Now, because it's exothermic, because our delta H is negative, this number must be larger. The energy released when bonds form must be greater than the energy to break the bonds. That gives you an exothermic reaction. All right? So this value is greater. All right? Okay, after the experiment, a student notices some undissolved product in the bottom of the calorimeter. Analysis shows the calcium chloride is contaminated with calcium phosphate. Calcium phosphate is not very soluble in water. How would the contamination of calcium chloride with calcium phosphate affect the enthalpy of solution value? Well, basically, the calcium phosphate isn't really going to do anything, so it's not really going to release any energy into the water, okay? And so basically, you're going to uh, have some energy, all right? You're going to have the kilojoules, but when you divide that by the moles, your moles are going to be larger than expected, or larger than actual moles of calcium chloride. Okay, so if this number is bigger, basically you're going to get a lower uh, delta H value. Okay, so it's going to be lower because your moles are going to be the actual larger than the actual moles of calcium chloride, and so you wouldn't get as much energy as you would expect with that much chloride. Okay, with that, with as you would expect to get from the calcium chloride, and the moles would be larger than actual, so that's going to give you a lower delta H. All right, so anyway, okay, calculate the molar solubility of calcium phosphate in pure water. So this is a Ksp problem. So calcium phosphate, solid, and it's going to break into calcium plus phosphate, and you'd have to have a 3 here and a 2 there, and we make an ice table. And so solids aren't part of our expression, so this is 0, this is 0. This is going to go up by 3x, so at equilibrium we're going to have 3x. This is going to go up by 2x, so at equilibrium we're going to have 2x. And so we could write our Ksp expression. Ksp is equal to calcium, and that's going to be to the third power times phosphate to the second power. All right, and then we can plug in our number. And so because the molar solubility is the X is what we're looking for. All right, so we take our Ksp number, which is 2.07 e to the minus 33 is equal to 3x to the third power times 2x to the second power. So we end up getting 2.07 e to the minus 33 is equal to 3 cubed. Don't go 3 times 3. That's a mistake I've made before. 3 cubed is 27 x to the third times 4x squared. And so then we end up getting 2.07 e to the negative 33 is equal to, let's see here, 100, that's 108 x to the fifth power. Divide both sides by 108, and then take the fifth root of that. Okay, remember on your calculator you can just go upper caret 1 over 5. That will take the fifth root of it. All right, and then so I end up getting that x is equal to 1.14 e to the minus 7 molar. That is the molar solubility. So now, once we know the molar solubility, which tells you the maximum number of moles that will dissolve in a given amount, well, it tells you the molarity, the maximum molarity you can make a solution at a certain temperature. But anyway, how many grams of calcium phosphate would dissolve in 200 milliliters of pure water? Well, if we have 200 milliliters of water, okay, now we know that the maximum molarity is 1.14 e to the minus 7 moles over 1,000 milliliters. See, that's there. I'm just putting the molarity. I'm breaking it into its components. Then I'm just going to change it to grams. So 1 mole calcium phosphate, and the molar mass is 310.18 grams. And if we do that math, we get 7.07 e to the negative 6 grams of calcium phosphate. Okay, in the experiment in part 1, above, the molarity of the calcium ion was 1.17. Would the student expect the actual mass of calcium phosphate dissolved in the water to be greater, less, or the same as the amount calculated in 2b? Okay, remember in 2b we were doing it in pure water. So let's just look at an ice table and see what would happen here. So calcium phosphate, and it's a solid. We put that in water, and it's going to break into calcium ions plus phosphate ions. And let's see here. Remember, solids don't count in our equilibrium stuff. So initial change equilibrium. So solids don't count. Now, the molarity of the calcium before the originally because of the calcium chloride, it was 1.17. Okay, phosphate is not a common ion. All right, but the calcium is a common ion. Now it's going to go up by 3x. This one's going to go up by 2x. All right, and so we're going to have 1.17 plus 3x, and right here we're going to have 2x. Now we could plug this into our expression that we just did on the previous page, or the previous problem. So we know the Ksp is 2.07 e to the negative 33. That was from the previous problem. And that's going to equal 1.17 plus 3x to the third power times 2x to the second power. Now, anyway, you could look at this and say, well, this x that this is going to go up by, and we kind of did it in pure water, it's not going to be a very big number. So basically we can drop this x right here. That prevents us from having to do some sort of difficult math. Okay, and so that's going to equal 1.17 to the third power times 2x to the second power. And if you go through and you solve for x is equal to 1.80 e to the negative 17 molar. Okay, now this is the molar solubility when there's already calcium in the water, not pure water. And if we compare it, so 1.80 e to the minus 17, and if we compare it to the other problem in pure water, so in pure water it was 1.14 e to the minus 7 molar. So you can see it's much less soluble in the calcium because of the common ion effect. There's already calcium in the water, so you can't dissolve as much. Okay, all right. So that's it. So the answer is, would you expect the mass to be greater, less than, or the same? It's going to be less due to the fact that there's already calcium. You're starting off with some calcium already dissolved in the water. Okay, then this question is kind of the same as the last one, except you got to use a different the molar solubility. So how much would dissolve in 200 milliliters of water? Okay, so we have 200 milliliters, and we know that the molarity is 1.17, so it has a different molar solubility. It's not in pure water. E to the minus, I forgot that one there, e to the minus 17 moles over 1,000 milliliters. There I'm using the molarity, which is the molar solubility, the maximum molarity you could make in 1.17 molar calcium chloride. Then we're going to change it to grams. 1 mole calcium phosphate, and the molar mass again is 310.18 grams calcium phosphate. And if you do all that math, you get 1.12 e to the minus 15 grams in calcium chloride. And if we go back, like I said, it was 7.07 in pure water, 7.07 e to the negative, let's see, I kind of forgot what that was, e to the negative 6, e to the negative 6 grams in pure water. So the common ion effect, having an ion of calcium already in the water before the calcium phosphate tries to dissolve, it's going to dissolve way less, okay? So that's kind of an example of the common ion effect. Okay, that's it for that video.